Thank you all for coming, and thank you for the organisers for the opportunity for me to present some work that my group has been doing in recent years on decontamination process monitoring. So just to start, a couple of disclaimers. So the opinions expressed here today are those of me as an active researcher in this group, not of my parent organisations, Public Health England or the Department of Health, nor of the National Institute of Health Research, who has funded some of the work which I'm going to talk to you about today. The thermostable adenylate kinase technology, which I'm going to talk you through, was invented in my group, and PHE would receive milestone and royalty payments if that technology was commercialised. That being said, all commercial decisions are down to the companies who've licensed the technology and not those of PHE. And as you can see at the bottom, we've worked with a number of commercial parties in either collaborative grants or fee-for-service type contracts. So what I'm going to talk to you today is some of the challenges around monitoring, particularly gaseous phase hydrogen peroxide decontamination processes, both in healthcare but also relevant to the pharma community as well. So I'm going to talk to you about biological indicators, Bacillus styrothermophilus spore strips, looking at where there may be not the most resistant organisms in the healthcare community, talking about thermostable adenylate kinase TAK technology, which is the basis of our rapid decontamination monitoring process. Some studies we've done in terms of establishing the equivalence of biological indicators and TAK systems, and just starting to talk through building a case for where these technologies might have value in terms of improving the monitoring of decontamination processes. Very brief introduction to my group. So my group is interested in healthcare-associated infections in general, and we have a variety of interests in infection control, particularly applied infection control in the healthcare systems. So we work on, for example, decontamination processes, particularly related to biofilms. We have technologies to do with rapid point of care and point of use detection, and that's actually where this work stems from. But also some interests in the evolution of escape pathogens and in antimicrobial resistance in general. And this was our introduction to monitoring of decontamination processes. We were involved in a Department of Health study a number of years ago now, who asked us to look at the levels of residual protein on several trays of instruments like this. And this was very much driven by trying to understand the potential risks of prion transmission. Now, don't be alarmed, this is an uncleaned dental scaler. This wasn't in one of these trays. But we were quite concerned about the level of variation in protein residuals in these types of trays, and particular instruments like this. So we could find several milligrams of residual protein left after cleaning, after sterilisation, just ready to go back to the patient on instruments like this. And that clearly had some issues around potential prion transmission risks. So I'm sure many of you have seen this before. This is the life cycle of a surgical instrument, a very complicated process. And I think coming at this with a clean pair of eyes, we were quite concerned that the major way you checked whether instruments had been cleaned properly was by visual inspection. And that still remains the gold standard today. And we and others have done studies to show that actually your ability to predict levels of protein soiling on instruments and the actual values you can recover in a removable protein are very discrepant. So your eyes are not necessarily a good predictor of cleanliness in this context. So we started to think about how you might monitor these sort of decontamination processes. It seems very unfashionable and very niche area to try and understand how you monitor cleaning of dental instruments or cleaning of surgical instruments. Now, the gold standard for many years, as you're probably aware, is an inhydrin. So an inhydrin is actually a measure of amino acids, not of proteins, and is relatively insensitive. So it's sort of the tens of microgram range if you apply this to even amino acids. But that remains one of the standards for monitoring the cleanliness of surgical instruments. If you go into a laboratory environment, we're very used to all sorts of fluorescent and spectrophotometric methods, things like SPR, which measures interaction with surfaces. And we use those in an analytical sense, but we think these are probably relatively difficult to see sitting in a sterile service department used routinely to monitor cleaning of instruments. Some of my colleagues based here in London and Southampton and up in Edinburgh have done a lot of work on fluorescent detection of residual proteins on instruments that, again, some of you may be aware of. But certainly we think the further to the right you go, the more sensitivity you get and the more predictive those systems are going to be of levels of residual soiling, but the more costly they are and the more difficult they are to implement in a rapid setting. So we went to talk to our local hospital. So Peter Wells was the Sterile Service Department Manager at Salisbury District Hospital, and we tried to work with Peter to understand what he needed in this context, because we thought by understanding the environment he works in, we'd be able to understand where the technology may fit and how it would fulfill his needs. And this was his sort of shopping list. He wanted a quick and easy test. He wanted it to be unambiguous, sensitive and specific, and traceable. You know, we're living in a world where there's a very significant audit requirement on many of the things we do, and the ability to download and trace the results was very important. So what we generated, and I'll show you in a couple of different settings, was a sort of 2-minute assay that could be used by an end user. So this isn't a specialist piece of laboratory equipment. We're looking at a fully quantifiable measure of decontamination processes. So this isn't a qualitative or subjective type of test, and that was important. The sensitivity is very good, and we can download all of this information into a PC so you can monitor trends over time. And again, we think that's very important. So this work was funded by the Department of Health. This is one of their old schemes, new and emerging applications of technology, and NIHR through their Invention for Innovation Fund. And this is the basis of the technology we use. This is one of my colleagues sampling a hot spring in Montserrat. Very glamorous life. Sadly, I'm a molecular biologist, so we do all this in a fermenter in the laboratory these days, and I've never been to Montserrat or anywhere equally exciting. But this is the base of the technology. We're using thermostable adenylate kinases. Now, these are ubiquitous enzymes. They're in every cell of every organism, and they're involved in maintaining the cellular energy balance. We use an enzyme from one of the bacteria that live in these sort of hot springs, so you can imagine the bacteria have to be remarkably robust to survive in that environment. And you find that a lot of the enzymes that they generate and they produce are also equally robust. So we can quite literally boil this stuff without losing activity. The enzyme, in the way we format the assays, generates ATP. Many of you will be familiar with the sort of luciferin, luciferase measurement systems that allow you to quantify ATP across a very long dynamic range by the production of light. So just to be very clear, because there's sometimes some confusion here, this is not an ATP test. This is not like surface swabbing and hygiene monitoring. This is measuring the function of these enzymes in the decontamination process. So we're looking at enzyme removal or inactivation as a function of the decontamination process. So we've done a number of studies over the years, and this is the basis of all of the decontamination monitoring work that we've done. So the TAK is a surrogate measure of cleaning and decontamination or disinfection. The test measures the enzyme that is either left at the end of a washing process or a cleaning process, or it measures a functional enzyme that remains unmodified by whatever your decontamination process is. So you're measuring the function of the enzyme. We can fully quantify that. These are a whole raft of different systems that we've used over the years. Reagents are off the shelf. And these are some of the test devices, which are the front end, the user end, of how these devices are used in healthcare and in pharma settings. I'm just going to show you a little bit of data on the cleaning agent, then I'm going to get on to talking about hydrogen peroxide. So we've published a number of studies. This just shows a study looking at a dental washer disinfector and looking at a range of different products here labelled A to H, which were used in that environment for cleaning dental instruments. We were quite surprised to find product C, for example, is essentially the same as washing in water. But there's a whole bunch of chemistries down here which watch essentially to the limits of detection of the assay. So those chemistries are very good at removing proteins, and actually 3 of those were actually validated for prion removal in studies separate to this. So this just shows you in all of these graphs what you'll see is the lower the bar, the more efficient the decontamination or the cleaning process is. So in all the graphs I'll show you, it's the same sort of readout. But we saw a very big difference in this setting. This is a dedicated laboratory setting, so we were very keen to take this out into the real world. And we had funding from NIHR to do a hospital trial, a field trial. So we looked at this technology in 6 sterile service units in the NHS, plus 1 site in the Netherlands, which actually runs 2 different cleaning processes in their systems. We were very keen that this was done as far as possible as an in-use study. So we didn't try and influence what went into the machines. This is normal daily service. To enable us to do that, we did quite a detailed risk assessment with both the SSD staff and the infection control staff. The team spent 2 days in each of those hospitals. We looked at a single automated washer disinfector, and we looked at 5 cycles. And we put indicator devices in every basket in those cycles, so we generated a lot of information about how those processes worked. This is all published in the Journal of Hospital Infection a couple of years ago, but just to give you a snapshot of this and how we think about the potential of this technology being used, what it enabled us to do was to really see differences in performance in different hospitals and within a single hospital. So most of the sites we looked at, we classify as Group A, artificially classify as Group A. So all of these sites were essentially cleaning to the limit of detection of the assay. So very, very good cleaning performance. No differences between the different washes, no differences between the different baskets. We had 2 sites which we classified in Group B. Again, they're cleaning very, very well. We're not making a judgment on how well the cleaning process is. It's really about how that process can be managed and traced. And what we saw was there were some differences. So these aren't all cleaning to the best possible standard they could do in that machine. And in this particular hospital, you would probably want the instruments that were processed later in the day, which were very, very low into the limit of detection, rather than the ones that were processed at the beginning of the day. So what we could see is there's a difference between the process, and it suggested there could be some improvements in terms of the management of that cleaning process. One site, the axis here is actually 10-fold bigger than this one. We saw very relatively poor cleaning. So it was still passing all of the international standards and all of the regulated tests, but actually comparatively it was cleaning much more variably than the other hospital sites. This technology is commercialised by a company called Biotac, and if you have any questions, I'm sure they'd be very happy to sort of answer those questions. So that experience started us to think about hydrogen peroxide decontamination. Now, we're aware that hydrogen peroxide decontamination is used very widely in pharma, and increasingly is being promoted for disinfection within hospital environments as well. Now, the gold standard, if you like, for monitoring those type of processes, either on setup or potentially in use, are spore strips. And if you look at the sort of performance characteristics of these things, there are some challenges. So at best, they give you a result in 24 hours if it's a gross fail, but it can be up to 7 days before you can really say that decontamination process worked as it should have done in this environment. You need specialist facilities. That can be just an incubator, but you have to take that spore strip, put it into a reaction vial with media and grow it out for that period of time, usually at an elevated temperature. Quantification is poor. It tends to be growth or no growth, by and large. And there is certainly a reputation in the pharma industry that these tests are relatively unreliable. And I'll show you an example of that a little bit later on. And again, thinking particularly around pharma, it's always seemed curious to me that you'd put a live organism into a setting where you want sterility or essential sterility. So we wondered if TAK could be used in this sort of setting. The other sort of products that are available, so I've talked you through the biological indicator story. You can buy chemical indicators for hydrogen peroxide, for example. Now, these are just chemicals that change colour generally in response to exposure to hydrogen peroxide. So they're not really measuring a biological function. They're rapid readout. You can have an answer pretty quickly. They're relatively cheap, but they're, again, qualitative. It can be difficult to read a test, so sometimes there's some ambiguity around the colour changes, and they're relatively insensitive to hydrogen peroxide. You can also have parametric release, and many of the hydrogen peroxide systems that you'll be aware of monitor hydrogen peroxide dose. They monitor or modulate the temperature and humidity in the room to try and ensure that you're getting efficient hydrogen peroxide decontamination. Those can be built into the machine. Again, you're getting an immediate readout if there's a major problem, but there's no measure of efficacy of hydrogen peroxide there. This is just measuring the environment that system is working in. And traditionally, hydrogen peroxide sensors have been problematic, and again, we've seen evidence of that in some of our studies. What's a biological indicator? This is the gold standard. So this is a definition taken from the US Pharmacopoeia, again looking at the sort of pharma industry, and this is how they define a biological indicator. So it's a well-characterized preparation of an organism that has a defined and stable resistance to whatever it is you're measuring, in this case hydrogen peroxide. Now, they're almost all, I think all of them are spore-forming bacteria, but the reason they're used is because they should be significantly more resistant than the normal bacteria, normal microflora within that environment. And I think you can kind of challenge that statement, as you'll see in a minute. This is how you buy BIs. So Geobacillus styrothermophilus is used for hydrogen peroxide. You have some different spore-forming bacilli used for ethylene oxide for dry heat. Steam is also styrothermophilus. And you'll see each of these has what's called a D value, and the D value is a logarithmic reduction value. So it's the time taken to reduce the population of that bacteria by 1 log, 90%. So, for example, if you have a D value of 2, you have a log reduction. Every 2 minutes, you'll reduce the number of bacteria in that environment by 1 log. So if you're looking at a 6 log reduction, that's 12 minutes, because it's at least nominally a linear relationship between time and inactivation. If you had a D value of 4, it would take you 4 minutes for each log reduction. So you'll see these commonly on the sort of devices you can buy for monitoring these processes. Now, significantly more resistant than normal microflora. This was a study done by some of my colleagues at Porton in the biosafety unit, and they looked at MRSA versus the gold standard spore strip. And what you can see immediately is that MRSA is more resistant to hydrogen peroxide in this particular system. Again, this work is published if you want more details. And the reason for that is that MRSA is a catalase producer. So the inference from this data is that catalase can reduce the level of hydrogen peroxide and allow some survival of MRSA, which is greater than, say, the gold standard, the most resistant organism that is identified in the pharmacopoeia. So that's one example. And the other example is biofilms. Now, these are very basic, very simple biofilms, which we've generated as part of some of our studies. They're not the huge mats of microorganisms that you may be familiar with, but these are the early stages of that. But you can already see quite complex interactions here. And certainly, if you look at how hydrogen peroxide penetrates into biofilms, penetration can be relatively poor. And that will limit the biocidal efficacy of hydrogen peroxide in these systems. You tend to also see an upregulation of oxidative defense mechanisms in biofilms. And again, that's going to compound any issues around poor efficacy. So you're very reliant when you're thinking about biofilm removal on efficient cleaning. And that's true for all hydrogen peroxide processes. The better you clean, the better penetration you'll have for hydrogen peroxide. If you have layers of organic material, then they will mop up a lot of the activity of a hydrogen peroxide system. So biofilms are probably more dependent on getting that cleaning right. So this was a study. We rented 2 different hydrogen peroxide systems. We installed them in one of our laboratories. We ran them according to the manufacturer. And we put biofilm tokens, very much like what I showed you initially, into those environments. We ran biological indicators over on the right-hand side, and I've kind of artificially divided the cycles up into percentages, and I've done that later on as well, because different hydrogen peroxide systems run over different lengths of time. So rather than make any judgment about which part of the process was more effective, we just divided it into 12.5%, 25%, 50%, and full cycle. And what you can see is biological indicators in this model are killed by around 12.5%. All of these healthcare pathogens are still alive at that point. So MRSA, Acinetobacter baumannii, which is one of our organisms of interest, Pseudomonas and Klebsiella are all alive at 12.5% in a biofilm. And you can see Acinetobacter and Pseudomonas right the way through to full cycle are still not killed by those processes in these systems. So this was system 1, system 2, slightly different. So the BIs survived slightly later. And again, Acinetobacter and Pseudomonas are surviving well beyond the BIs in this particular model. So again, the biofilm life cycle biofilm mode of living for bacteria is certainly a way which can, certainly a feature that can impact on efficacy of hydrogen peroxide processes, challenging this idea of whether spore strips, biological indicators are really the gold standard. So, can we look at using our TAK system, our thermostable adenylate kinase system, as a way of measuring hydrogen peroxide efficacy? So I've already sort of talked you through some of the issues around spore strips. If you set against that, we have a test that runs at 2 minutes, is simple to operate at point of use. We have, say, a number of systems which we could use in this particular system here. Is fully quantifiable and reproducible. And we can also potentially sterilise these things at point of use. So particularly for the pharma industry, that may be more important than for healthcare. So this was the first bit of data we generated. Could we get a dose and time response with hydrogen peroxide activity against our enzyme that suggested that this sort of test would be viable? And what we see is a dose and time dependent inactivation of the enzyme. Now we can kind of rationalise this. This is a schematic of the sort of structure of these enzymes. And they have what's called a lid domain, and they have an AMP binding domain that bind the two substrates. And what we think happens is hydrogen peroxide actually interacts with specific amino acids in this loop that are essential for catalysis, and therefore you're getting a really predictive dose-dependent inactivation of the enzyme that makes you see these lovely sort of linear kinetics. So we set about doing an evaluation of this in the same sort of environment. Again, we looked at 2 different commercial whole room decontamination. These are whole room systems in this setting. We ran TAK indicators versus our BI strips. And we did the study in 2 ways. We looked at a time course or partial cycle study to try and look at how long the various indicators survived in the process. And also standard practice, certainly in the pharma industry, is to look at position. So there are positions in a room which would be more difficult for hydrogen peroxide to get to in terms of it being able to kill microorganisms. So we had to look at that as well. There's quite a lot of data on here, so apologies, but I'll sort of talk you through it. So the graphs are the same as you've seen previously. The lower the bar, the more effective the hydrogen peroxide has been at decontaminating and activating the thermostable adenylate kinase. There are 3 studies, and again, I've segmented this into 12.5% of the cycle, 25%, 50%, and full cycle. And we ran 3 independent runs. And you can see there's some variability in terms of the TAK levels, and also in terms of the biological indicator values. Now, first thing we did here was actually run a set of BIs from a manufacturer that failed every single cycle. So we don't think there was anything wrong with the hydrogen peroxide cycle. We think it was running properly and correctly, but there was a manufacturer fault in the BIs. Now you can imagine the sort of implication of that in a pharma industry if every one of your cycles is being failed, even when it's running properly, and similarly in a healthcare setting. So if you like, it was almost a validation of why we started to think about this in the first place. We brought in another manufacturer of BIs, and they performed absolutely fine. Now, in the red trial, all of the biological indicators are killed by this time point. Okay? So this corresponds to this adenylate kinase level here. In the blue trial, they survived out to 25%, so they were killed by this point. But in the green trial, they were only killed by this point, 50% of the cycle. So there was some inherent variability within the performance of that hydrogen peroxide decontamination process in the setting we were looking at. But what we found was very nice is we can sort of draw an artificial threshold across here at about 500,000 relative light units, and that is very predictive of when these cycles reach the point they've killed all the biological indicators. So the red one drops below this bar here, and this is where all the BIs are killed. The blue one is by here, and the green one only just by here. And that corresponds to where we're seeing BI growth, BI kill. Now, it's taken us up to a week to get to that data for BIs. We're generating the TAK data in about 2 minutes. And again, this is something we're very keen to explore. We took that same decontamination process and looked at position effects. Now, these are all full cycles. These are all run right to the end of the process, typically about 80 minutes. And most of the BIs were killed. Only in one of the runs, and actually only one of the biological indicators, did we see any survival of biological indicators of the spore strips. And it happened to be this one. which is well above this artificial threshold value that we put on there. And actually, we didn't see it fail until 5 days after the process. Now, within the spore strip manufacturers, that's a fail. But you don't get that information until very late in the process. Now, what do you do with that? If something fails that late, how do you deal with that information? And again, we think there is a value in supplementing that information with a test that let's say, well, actually, maybe I need to rerun that process because one of my TAK indicators has suggested there's quite a significant survival here. Similar story, this is the second system. Now, it just so happens that the 25% point sits very close to that threshold that we've drawn. So one of these groups, we see BI survival, and 2 of them we see BI kill at this point. So it just happens that 25 point is very, very close to where the threshold value is reached. But again, it's encouraging us to think, well, actually, if you've killed everything, it's down here, you can very clearly demarcate that and identify where there are potential problems. Now, in the position study in this setting, in this system, we saw no survival at all. And again, all our TAK values at the end of the full cycle are very low, so reinforcing that that process has been running correctly. So we've taken this on. This is a slightly different setting, so the people in the front row might be able to say this scale is slightly different. That's a function of the luminometer we're using in this setting, and also that we're using an isolator rather than a whole room application. And what we set out to do here was to simulate what would happen if you had the wrong dose of hydrogen peroxide. So if the bottle had been improperly stored, if you'd not put in the right amount, or the system hadn't put in the right amount, could you detect that in this system? And what you can see in each case, so again, you've got fractions of cycles. These are just identified in slightly different ways here. You can see you get, again, a dose dependence in activation depending on the concentration of hydrogen peroxide. And again, if you just follow the red lines or the green lines, you get, again, a time dependence in activation. We put on a very similar sort of threshold, and again, here's the sort of break point. So at 10% hydrogen peroxide, even if you run it for a full 80-minute cycle, we're not seeing an activation of the BIs, and we have a value that's above the threshold. Again, the red one is above threshold, but very close. The green and purple are just below. And again, that correlates quite well with the inactivation of biological indicators in this model. So not only can it sort of monitor routine processes, but it can also see when things are going wrong. And we're adding to this data at the moment to look at other settings which might impact on the efficacy of hydrogen peroxide. So this is a question, really. Where does this AK monitoring process fit in terms of hydrogen peroxide decontamination processes, either in pharma or in healthcare? There's clearly some potential value in terms of reduced turnaround time. So if you know there's a problem, you can act much more quickly with this system. If you're waiting for the biological indicators to grow before you act, that can be quite a slow process. So even if you supplement that testing with this sort of device, there's potentially some value. And I think it's also very reassuring to have that immediate validation that the process has performed in the way you think it has, as close to real time as you can. Thinking about both industries, there are going to be some regulatory hurdles in terms of what this sort of technology needs to achieve and the sort of burden of proof we need to develop. But again, if you go back to this shopping list, there's a lot of positives here in terms of this rapid assay, this quantifiable measure of efficacy, because I should restate that. This is both quantifiable and can be downloaded. So if somebody wants to come back and audit that process in the future, then all that information can be stored in a way that can be looked at. We've got a lot of QC data around the manufacture now. We're working on that, and we're starting to build this story around the correlation between our adenylate kinase indicators and 6-log spore strips, because that's really the gold standard still in the industry. We used to apologise for this being an enzyme on a stick, because that's essentially what the basis of the technology is. But actually, it's proved to be a very versatile system. So I've shown you some data on cleaning. I've shown you some data on hydrogen peroxide decontamination. But there's a lot of other processes which might be relevant for different industries that we can also monitor using this device. So we've modified the surface of the strip, and we can see changes of that predicted by the TAK. We've looked at plasma decontamination systems that really strip materials absolutely bare. We've looked at processes that damage proteins. So, for example, proteases that digest proteins we can monitor using this technology. Formaldehyde is still used for laboratory decontamination in some settings. And then we're very interested in exploring this around high-level disinfection. So we have data showing that chlorine or chlorine dioxide will again inactivate the enzyme in a dose-dependent way. Hydrogen peroxide showing you we've done some work on ozone, peracetic acid and peroxygen. And reactive amides, based on this data from formaldehyde, is also something we think is likely to give you a dose-response curve that could be used for very rapid process monitoring. So, this was the question I started with. Is there a better way to do decontamination monitoring? And hopefully what I've shown you is there are challenges with the way we monitor or rapidly monitor decontamination processes. And I've given you a couple of examples of that. But particularly thinking around gaseous decontamination, if this is something we're relying on as a major component of our infection control procedures, maybe we need to look at how this system is monitored on routine use. And maybe there are some advantages in the sort of technology that I've showed you. I've talked you through the TAK indicators. I've shown you a little bit of that data. There's a growing body of data now where we can build that story around the correlation between these devices and BIs and other microorganisms. And we're starting to build a case that would support the use of these tests as an additional layer of quality assurance around decontamination processes. The technology is being commercialised by Protac Scientific. Some of their representatives in the audience, they have a stand through in the main building, and I'm sure Phil and colleagues would be very happy to discuss with you if this is of interest. A variety of things, but things like early release of indicators, trial studies, the sort of benefits and opportunities that the technology might offer, and hurdles to implementation. But we're not unaware that this is going to be quite an interesting discussion with a variety of stakeholders. And finally, just to acknowledge the people. So again, my colleague Neil McLeod has led most of this work for the last 3 or 4 years and has performed amazingly with this technology and moving it forward. He's supported by Mel Clifford in my group. Some of the early work was done by Lucy Bock. And just to acknowledge funding from I4I, Public Health England's Pipeline Fund, and now commercial sponsorship working with a variety of companies. Thank you.